guys, it's Nicole here again with another tutorial. This time we're talking about BCD. It stands for binary coded decimal. If you've ever had a watch, a stopwatch, alarm clocks, gauges in vehicles sometimes, like temperatures and things like that, typically this is the display they're going to use. It's something you may not have thought about, or I know I never really gave it much thought, but it's a very simple scheme that allows an operator to have an interface between a circuit, so we can see certain values. So in an airplane, it might be an altitude on the cockpit. It'll allow you to actually display a dial and things like that. We could turn a dial and see our altitude readings, things like that. So heading in an airplane, for an example, a watch, and like an actual digital watch, not a smartwatch, but a digital watch, like the old school digital watch. It's going to use something like this. And what you see on my screen right here is an example of BCD. So it basically is a very simple scheme that uses 7 segments, A through G. So A, B, C, D, E, F, and G. And it works by turning certain segments on and certain segments off. BCD uses 4 bits per character and can represent the values 0 through 9. So it does not make use of all those characters, though. We're going to see that here today. So let's go ahead and get started. So for this example, we're going to start with the number 1. So I'm just going to, let's say I want to convert the number 1 to BCD. So we want to convert the number 1 to BCD. So here we have our number 1 here. For some reason, my pen keeps changing on me randomly. So okay, here we go. So we got our 1. So how does this work? Well, to convert number 1, I have 4 bits for that character. So we're going to say 2 to the power 0, 2 to the power 1. You guys probably remember this from my previous tutorials. 2 to the power 2, and 2 to the power 3. So what does this give us? Well, it gives us, again, 2 to the power 0, exponent 0 always gives us 1 for our scale. So here we have 1. 2 to the power 1 is 2. 2 to the power of 2 is 4. And then 2 to the power 3 is 8. So you can see where we're going with this. So we got our scale going right here. And then to make number 1 happen, in BCD, we're going to turn the 1 position on over here, and we're going to turn all these positions off. So what we're going to get for this number 1 in BCD is going to be represented by the bits, the binary bits, 0, 0, 0, 1, just like this right here. And we'll put a little base 2 there. So something like this, right? Now what exactly does this do? Well, basically, we want to be able to change this number 1. So basically, these 4 bits, this 0, 0, 0, 1 binary, is going to go into an encoder. So it's going to go into a little encoder, like at the circuit level. And what it's going to output is basically this. It's pretty genius. So now to show this a little better, what I'm going to do is I'm going to color code this. So let's do this. So we're going to go, so to make a number 1 happen here, I'm going to turn this position on and this position on, just like this. Just like what we did there. All right. And when we do that, so basically think of it like this. We have segment A. Oops. That's hard to see. That's really hard to see. Sorry, guys. So we have in our encoder, the output of this little encoder process is going to be, we have a segment A, segment B, C, D, E, F, and G. Something like this right here. So the way this works is we're going to, the A position segment is going to be turned off, so it's going to be a 0. The B is turned on, that's going to be a 1. The C is turned on. The D and all the other characters are turned off, so the remaining characters will be 0s. So what this means is whenever this goes into the encoder, these 4 bits, it's gonna basically output these bits here, this 0, 1, 1, 0, 0, 0, 0, and that's going to tell these segments to operate just like what you see here. Pretty cool, isn't it? So you'll only ever see 4 bits though. So we only see 4 bits. And because we can only represent the values 0 through 9, you'll never see any of these values. You'll never see 10 through 15. You'll never see any of those other, because remember, there's 4 bits, so there's the total possible values. We actually could account for like 10 through 15, just like we do with hex. But in this case, that's not going to happen. We're going to stop at 9. And so basically, the highest possible value you could represent in the system is 9. So, and I'll show that here. So what we're going to do is, let's change this again. So we're going to go up here. I'm just going to erase some of this here. Oops. Let's erase this here. Maybe let's just erase this over here like this. I'm going to leave the ABCD there, but we're going to change our number. So instead of using that number there, what we're going to do this time is now we're going to change this like this. And this time we're going to represent the value 9. So again, so what is 9 going to be in BCD? So let's start with our number. So we have 9. That's our number we want to convert. So just like before, let's start with our scale. So again, least input side over here, going toward the most input side over here, just like this. And then we get our scale going. So 1, 2, 4, 8, just like we've been doing all along, just like we did in the last example. We want to make this value happen. So we're going to turn the positions on to make that value. So 8, we're going to turn that on because 8 will get us to 9. If we add 4, that's going to put us over 9, so we're going to zero this out. Same with 2, so 8 plus 2 gives us 10, that's too much. And 8 plus 1 gives us 9, so we're going to turn this position on. So 1001 is our value for 9. So 1001 is the BCD equivalent of 9, and this is the highest possible number. So what this is going to do, just like we did before, I'm going to color code this again. Just like before. So we want to make a 9 happen, so we're going to color code this just like this again, just to make it easier to see. So there's our number 9, just like this. You can see we have a 9 right there. And back over here, and so on the output, the 1 is going to be, so we're going to have a 1 for the A segment, 1 for the B segment because it's turned on, 1 for the C segment because it's turned on, 1 for the D segment because it's turned on, nothing for the E segment, 1 for the F, and 1 for the G segment. So this becomes our output. That's actually what's going to, these are the values that are going to cause the reaction of that display. So in the cockpit or whatever the display is that's trying to give us the number back, that's what's going to give us that display. Pretty cool, isn't it? So now the question usually comes up, and I'm going to talk about this real quick. So one question that sometimes comes up with a lot of folks when they see this for the first time is this, and that is, what happens in the event that we have something like this? Like, what if we had, let's say, for example, we had the number 12. So let's say let's say we have an inadvertent, something happens in the transmission, something goes wrong, maybe you're transmitting these bits, something goes wrong, so we end up with this. So, well, if we were to convert this number over here to 4, 8, this actually is 8 plus 4 is 12 plus 1 is 13, so this is actually 13 in decimal, in base 10 decimal, right? So, well, we can't make a 13 happen here. I mean, there's like no way to do that, right? So basically the way this works, it's pretty genius. So anything like the number is 10, so 10 would be, and I'm going to write this over here, so 10 would look like this, so it's going to be 1, 0, 1, 0. That would give us 10. 11 would be 8, 1, 0, so it's 8, like something like that. That would be 11. So any of these patterns that I'm putting up right now would be the same here. So these are all like non-existent here. 13 would look like this, so 0, 1. That would give us 13 in decimal. 14 is going to look like this. That's going to be 14. And then 15 is going to be like this. So basically, all of these patterns that we see that I'm putting up right here would all have the same reaction. So basically, the way this works is it's just going to zero all these out. So if this comes in, like if we get any positions that it can't actually display, what the engineers do is they just zero all of these bits out, so it doesn't actually do anything at all. So anything. So if it's if there's an inadvertent bit error or any issue with the system, like and we get something like this, we'll say this is an error bit right here, it's just not going to display it. So it's going to on the output, it'll just output zeros for all the segments and not turn any value on at all, which registers as an error essentially. So if you think of it that way, so that's a question that came up. It's come up a few times, so I just figured I would explain that. So, but that is BCD in a nutshell. So that's the idea behind it. Pretty simple scheme overall. So I hope you learned something. Keep practicing, and we'll see you on the next tutorial.